Hello, everyone. Welcome to the webinar, Risk and Criticality, Innovating for Raw Materials Security. My name is Jianchen Yu, Senior Director here at Lux, and I will be moderating today's session. Presenting today is my colleague, Ian Reinhardt, Associate Research Director here at Lux. Now, throughout the webinar, you can type any questions you have in the questions box on your screen. Time permitting, we will answer all the questions that we can. In the event we are not able to answer your question, please do not hesitate to email it to questions@luxresearchinc.com and we will get back to you shortly. Now, if at any point you experience technical difficulties, such as a frozen screen, simply refresh your browser and check that your internet connection is strong. Now let's jump into the presentation. Over to you, Ian.
Thank you, Yancheng. The task of navigating scarcity is daunting, and with ongoing disruptions to global trade, it seems more difficult than ever. But the history of shortages is also the history of innovation. So before I get into our latest research, I want to take you back in time to talk about a critical raw material, and that's whale oil. In the 1800s, burning whale oil in lamps was a common form of illumination, along with candles. And whaling fleets went around the world through the seven seas to hunt whales and process the oil into whale oil. But the more that they hunted, the more that these stocks went into decline, and the whaling fleets became less profitable and less efficient. And at the same time, innovators were looking at natural hydrocarbons as a potential replacement to whale oil in lamps, and these escalated through the mid-1800s. And then towards the end of the 1800s, as whaling really went into decline, petroleum production and kerosene took over. And then, of course, the ultimate disruption, the iconic symbol, the light bulb, and electricity became the common form of illumination. So in this case, of a critical raw material, it was innovations that resolved the shortage. So as I go through the talk today, I want to pose a question for you to consider. Are you hunting whales, or are you working on a light bulb? In my talk today, I'll first set the scene with important context about the economic and policy landscape. Then I'll explain Lux's raw materials criticality framework, the methodology, how it works, and more importantly, what you can learn from it. Then we'll do a deep dive into 4 innovation strategies that can help you put this concept into practice. So first, the context. When we talk about critical raw materials, the topic that tends to dominate conversation is critical minerals. And as you can see from the chart on the right, the concentration of production is really, these supply chains are heavily concentrated in just a few countries. In many cases, the top 3 producing countries account for 80% or 90% of world production. And it's not just the raw material, the refining stage as well is highly concentrated. You see these orange diamonds that are overlaid on the bars. That's the percentage of refining that occurs in China. So the refining stage is also highly concentrated. For global corporations, accessing critical raw materials is not getting easier. Countries are returning to old ways of thinking. It's hard power, realpolitik, no longer the trend toward efficient, low friction global markets. Using natural resources for political and economic leverage is the phase of the day. And all this creates problems for the private sector, for manufacturers. The nickel supply chain is a very clear example of this. In 2020, Indonesia banned the export of raw nickel ore so that they could take advantage of their strong production and force businesses to move their refining capacity onshore. And this was highly successful. Indonesia has edged out higher cost locations like Australia that just can't compete on price. And now Indonesia controls about 50% of the world market for nickel. And the government's looking to promote this policy further into downstream industries like EV battery manufacturing. But as you saw from the chart, the really big player here is China. Even in the supply chains where China is not the top producer of the raw material, 50% or 70% of the refining takes place there. And in overseas supply chains, all that new nickel refining capacity in Indonesia, who do you think is building those plants? It's Chinese companies. So in the ongoing trade conflict with the United States and in the past with Japan, China has banned the export of rare earth minerals as a means of economic leverage. But it's not just raw materials. Recently, China has also halted exports of extraction and refining technology. This somewhat odd substance you see in the picture is a lithium adsorbent used in lithium extraction. China banned the exports of lithium adsorbents in January. Now, to be clear, I don't want to villainize China. I don't think they have an evil agenda. They're just playing the game, and they're playing a strong hand. This is the context in which you must operate, and that's why you need a framework. So I'm pleased to share with you today Lux's raw materials criticality framework. Let me explain to you how it works. When you use this method, you're going to look at a particular system or component or a product and chart the key material inputs to that. So each of the dots you see here, like silicon, aluminum, copper, these are the inputs to solar photovoltaic power, so solar PV. This is the chart for solar PV. On the vertical axis, you see a measure of supply risk, which you might think of as volatility. And then on the horizontal axis, criticality, which looks at the balance of supply and demand. So let me break it down for you. Supply risk. This is the measure of the resilience of the raw materials supply chain based on its geographical spread and the stability of its producers. It's a two-part score comprising a quantitative measurement of the spread of producers among very few or more countries, and then a measure of the country's governance based on the World Bank's governance index. So is this a country that's more prone to corruption or political instability, where a single country could really alter the picture for supply of a material, or even a single leader in a single country? The horizontal axis, criticality, that's a measure of the raw material required to meet projected deployment of a technology in a certain scenario. So for the purpose of today's talk and in the report that Lux will be publishing shortly, we are using as a baseline the IEA's net zero energy scenario for 2050. So what will be all the components, systems, elements of the energy transition that will be required to reach net zero in 2050. Taking that material stock that will be required for that deployment and build out, then you divide it by 1 year of global production for that material. So a score of 1 on criticality means to reach the scenario, we will need to use an entire year's worth of production of that material. So it's a relatively rough measurement, but at a glance, it can quickly tell you whether there should be no supply constraints or whether there will be real challenges in meeting that future demand. It's a very intuitive framework, but I think a quick review will help us emphasize these points. The top half of the chart, these are dots that represent high supply risk. So material that is charted there is going to be more volatile, highly concentrated in one or a handful of countries that tend to have weak governance. And then conversely, on the bottom half of the chart, lower supply risk, a very diversified spread of producing countries, and those tend to have higher governance. Similarly, on the left, low criticality. There should be lower to no concerns about meeting supply in the future scenario. The requirement does not exceed 1 year's worth of global production. However, on the right, and especially when you get into higher numbers, 5, 10, and beyond, that raises concerns about the criticality, where future demand simply just may not be able to be met by the supply. And being good analysts, break it down into quadrants for you and give a headline, a bumper sticker of sorts that just quickly summarizes the scenario for materials plotted in that quadrant. On the top left, it's supply volatility. Bottom left, long-term stability. Top right, growth limitations. And then lower right, impending shortages. But what does that tell us? We need to turn the framework into action. So for the next part, I'll go through 4 innovation strategies that can help you in your role think about how to mitigate risk and put your company's growth on a foundation of resilience. Okay, so let's look at the first one. Or excuse me, before we get into them, a quick review of how the the process can work when you're plotting your products on the chart. First, you'll look at the location of dots and understand where is there a concentration, where are the key materials plotted. And then that will generally organically lead you to one or more of these 4 innovation strategies that I'm going to describe. You'll notice that there's not an arrow going from one quadrant to a certain strategy, but rather a broad approach, because these strategies correlate with certain quadrants, but it's not a one-to-one mapping. The reality is that a particular strategy may work well for multiple quadrants and multiple types of raw materials. So you need to first examine the chart in question and understand the best approach or approaches. So let's do that. For the first example, we're looking at solid oxide electrolyzers. This is one of the several types of electrolyzers that is being used to produce green hydrogen. Now, all of these materials have relatively low criticality scores. That's good. And many of them are in the lower left. But you'll notice that silicon, yttrium, lanthanum lie above the center line in the quadrant of supply volatility. The production of these materials is concentrated in just a handful of countries where governance may be lower. So your supply chain will be at risk of unpredictable disruptions. Now, the operations group can stockpile the material. Sure, that's a good start. But what can you do in the innovation function to mitigate this risk in the coming decade? One approach is develop novel sources, innovations that can supply critical raw materials from wastes or untapped resources. And I think the clearest and most obvious near-term opportunity here is in extracting high-value minerals from waste or industrial byproducts. The picture on the left shows a pilot plant in Australia that's scaling up a system to extract magnesium from coal fly ash, the residue of power plants. The second example, deep sea mining, it may seem a little bit far out, but I think that's exactly the type of high risk, high reward bet that companies need to take periodically. It's well known that there are trillions of dollars of critical minerals on the seafloor, many in these potato-sized nodules, but it's both a policy and technical challenge. Currently, there are policy limitations on commercial exploitation, and that's largely due to the very well-founded concerns about environmental damage to this fragile ecosystem. So this could be an opportunity for technical innovation. Can you combine the latest advances in AI, robotics, undersea vehicles to develop a system that very carefully and precisely, without damage to the environment, is extracting these nodules? I think that's a really interesting opportunity. Then on the right, an even more exotic approach, phytomining. That's engineering plants to extract minerals from the soil in say, areas with a high nickel concentration in the surface layer. Then you harvest the plants and consolidate the mineral in bulk. It seems a little bit crazy, but the startup Genomines just raised $5 million to further develop this approach. So it could be worth monitoring. Now, as I said earlier, we can use the examples from history to inspire us to show how this type of innovation has worked before. So the first flashback is about aluminum. In the 1800s, as manufacturers began to appreciate the great properties of aluminum, it became extremely precious. And that's because the only source at the time was the mineral cryolite, which was extracted in Greenland. And aluminum became more precious than gold. But then, through innovation, the Hall-Héroult process became possible to extract alumina from bauxite, a very common resource. And then, with bauxite reserves all around us, aluminum became one of the most common materials in the world today. Okay, let's look at the next example. Alkaline electrolyzers, another way to produce green hydrogen. But here you have only silicon over the line, and then the rest of the key material inputs in the lower left. This is the happy place. But that doesn't mean you can take a nap. There are still opportunities here. And that's why we highlight material optimization. How can you get more value with less material? Often it's the catalysts that are the main need for the most scarce materials, especially rare earths like iridium. And we've been talking to quite a few material informatics companies that are really focused on this problem. For example, you see here product from Matic, which is developing a lab on a chip approach to very quickly discover and test different catalysts that could be iridium free or have much lower loading of iridium, thereby bypassing that concern. In the middle, I'm taking an example from the food and beverage industry. This zoomed in image you see, those are tiny sugar crystals. And you'll no doubt notice the bubbles inside them. Scientists at Nestle developed a way to produce sugar that's aerated so that the tongue tastes equivalent amount of sugar, but the body ingests about 30% less. So you're getting the same function with less material. And in this case, it's also better for your health. Could you apply the same principle to your products? Then on the right, thin film deposition, relatively mature technology, but one that still has potential to be applied to more cases and more products. Turning back the clock, the mandate for catalytic converters on cars had a welcome impact on air quality in the middle of last century, but as it rolled out, it created a major supply-demand crunch for platinum. Companies eventually solved that challenge through R&D, developing blended catalysts that replaced platinum to a large extent with palladium and rhodium. Great. Now for the scary corner. This is the chart of NMC batteries. This is a type of lithium-ion battery that has a high quantity of nickel, manganese, and cobalt. And you'll see here rather high criticality scores, extremely high in some cases, and then also volatile supply for graphite and cobalt. Cobalt practically defines the top right corner of the chart here. There's really only one supplying country, and there's very low governance. So what can you do about it? Well, we recommend the strategy of alternative materials, innovations that can functionally replace a material. I'd highlight alternative chemistries. Lux has published a robust body of work, especially on alternative EV battery chemistries, but that's not the only case where that applies. This picture here on the left is the startup Niron Magnetics that's developing permanent magnets that do not contain rare earth elements. Synthetic replacement. Can you produce a materially similar product through another production pathway? The example I've pulled here, a little bit out of the box, bio-based concrete. These are a variety of startups are working on approaches using either microalgae or bacterial production to produce a material that has the equivalent strength and durability of concrete, but using a totally different supply chain. So this is a way to synthesize the material that may avoid some material risks. And then on the right, steer clear. Just don't do it. This may seem like a fairly obvious recommendation, but I think there are some layers here that are worth exploring. So for this product in question, NMC batteries, we're already seeing producers start to wind down those product lines. And it seems clear at this point that they're unlikely to occupy the position projected by the IEA in that net zero energy scenario. There will be other ways to achieve that. But what if you're supplying, say, cell packs or electronics for NMC batteries? Then your company's caught out. So it can also be quite valuable to use this framework to plot your customers' products so that you understand the material challenges they're facing and can stay one step ahead as you develop your own product portfolio. Because within a certain category, say batteries or electrolyzers, winners and losers over time will shift, of course, the market structure and even material demand in that sector. Looking at history for inspiration, perhaps one of the most iconic examples of a synthesized product is rubber. Up until World War II, about 85% of all rubber products were made from natural rubber. You can see here a picture of a rubber plantation. But when Japan cut off the United States supply from Southeast Asia, that kicked a national R&D effort into overdrive. And very quickly, scientists were able to discover a synthetic pathway, the styrene butadiene synthetic rubber that we know today and is extremely common in the market. So let's look at our fourth example, going back to solar photovoltaic, solar PV. You can see here silicon in the top right, many materials placed in the lower right. And then you may also notice a couple commodity materials, steel and concrete in the center. This framework is not only for critical minerals, but can be used for any material input that you consider could be a bottleneck. Through the post-pandemic period, especially 2021, 2022, as economies were opening up and economic activity was resuming, we heard very often our conversations with startup CEOs and innovators scaling up pilot projects that the real challenge was they just couldn't get the basic materials, the ducts, the pipes, the wires to build these new facilities. So in certain products or systems that have a large infrastructure requirement, things like steel and concrete could potentially be supply concerns. Okay, so what can you do in a situation like this? Well, the strategy we recommend, recycling and circularity. How can you get the most out of the resources that are already in circulation in the economy, maximize the recovery of those products for future products? On the left, a very obvious approach would be novel recycling technology. Now, this is there's more upside here for technologies like EV battery recycling and rare earth element recycling that are still immature, where those supply chains are being developed as we speak. The picture here is a British university scaling up a novel rare earth element recycling process. In the center, this is a concept that seems relatively simple and there's real payoff here, but it can be tricky to put into practice, and that's redesigning your products for circularity. This image is from a BMW concept car that has a threaded wire assembly for the seat instead of adhesives. So at the end of life, you just pull out the wire and the various materials, the metals, the polymers, the textiles separate cleanly, facilitating complete recovery. To reuse and recycle the materials in your products, rethink the attachments and use more mono-material pieces. And third, business model innovation can play a huge role in creating value. In so many cases, it's the collection step that's the most difficult. Can you create a consortium with the right incentives to develop efficient logistics among the partner organizations that will gather and centralize materials for recycling? The visual here is a partnership from Solvay for EV battery recycling. And we can easily take these circular approaches for granted, but thinking back to the middle of the 20th century, it wasn't until then that the electric arc furnace was invented and steel recycling became commonplace. Up until that point, pretty much all steel production was primary production. And it's hard to imagine how we could have achieved the current level of economic growth without being able to efficiently recycle steel. So can your company pioneer the same type of breakthrough innovation that becomes a foundation of modern economies? Great, so we've looked at all the 4 strategies which derive from the analysis of the raw materials criticality framework. The location of the dots and the materials in our products leads us to emphasize one or more of the 4 strategies, depending on whether we're concerned more about supply volatility or expected shortages or both. Now, these aren't mutually exclusive, and you can pick and choose elements of each. It's a toolkit. The key point is to understand your critical raw materials and to minimize the risk. Because when you carry out the right strategy, you put your growth on a foundation of resilience, and that's the shared goal. So I'll finish today by reviewing a few key points from the presentation. First and foremost, use the strategies and approaches I've outlined to build resilience. The right investments, R&D projects, and partnerships will address the supply risks that you face. Second, it's not only the more exotic materials that can be bottlenecks. As I mentioned, commodity materials, base metals, steel, concrete can become problems or even have high criticality scores depending on the requirements for your projects. And third, monitor the shifts in demand and within a particular way of solving a problem. If there are multiple systems that can deliver the same product, so we saw through electrolyzers, there are several different types of electrolyzers for producing green hydrogen. The shakeout of winners and losers in that category will determine market demand and will also help you project where you should be making your own product investments. So that wraps up my prepared remarks. Thank you very much, and I look forward to taking your questions.
Thank you, Ian. As he mentioned, we will now be taking questions that you may have on the presentation. And of course, you can type those directly into the questions box on your screen. As mentioned earlier, if we do not get to your question on this call, someone from Lux will be in touch with you after the webinar. We got a couple questions coming in, and I think the first one is, I think many people are asking the same thing. Do you have to use the net zero 2050 projections? It seems like that was the baseline for a lot of the examples here.
No, it's a very flexible framework. That's the one that we've used. We think it's a very good illustrative example, and of course, backed up by a strong body of research. So it's a good starting point, especially for that mid to long term view for innovation investments. But you can use your own projections. For example, Lux has done a look at the direct lithium extraction (DLE) capacity and project forecast through the 2030s. So if you want to think about, okay, what's the future for lithium extraction, you can use that forecast or another one to understand which type of rock or brine this is coming from and which type of systems will be used in DLE, and then model those out one by one to know what type of inputs will be required to make this a reality. And then you can understand from that forecast what could be some challenges or risks in the scale up of DLE around the world. So it's just a matter of making sure you have a solid forecast that helps you project out the material inputs, and then you can use it in a way that matches your company's requirements and priorities.
Nice. No, thank you. And another question here in the question box, and I'll add a little more color to it, but I think one of your key takeaways was for our attendees to think about their critical minerals and material strategy when they think about this framework. Can you use the framework in the opposite way? Can you use a framework to find new business opportunities instead?
New business opportunities, you can. I think, yeah, the tool itself is not is more designed to understand risks and to mitigate those. But if you think about it as a material supplier perspective, by kind of reversing the lens, then it does become a way of looking at new material opportunities. So we work with a lot of chemicals companies. If you're supplying a particular type of polymer, maybe a specialty polymer, and you understand the component breakdown of your customers' products, you can do the same thing and model this out. You can use the framework, think about what will be the requirement for those to scale up as expected through 2030, 2040. And then by plotting the dots in the same way, you can understand what that market landscape would look like in certain sectors, whether it's, say, the mobility industry, what polymers will be required for the vehicles of the future, and that the position of those dots, especially ones with higher criticality scores, will tell you, yeah, there's going to be more demand than supply here. So this is a good opportunity for us, especially looking at things on the right, maybe more, less the vertical axis, but especially the horizontal axis. That's a great way of identifying new market opportunities. Yeah, I think that would be another way of applying the framework.
Excellent. Very versatile. Well, looking at the time here, thank you, Ian, for today's presentation. To all the attendees, that concludes our webinar for today. As always, the slide presentation and recording from this webinar will be sent to you all via email today. And as you leave the webinar, you will be prompted to complete a survey on today's presentation. We'd greatly appreciate any feedback you may have to help inform and, of course, help improve our future webinars. In the meantime, please take a moment and check out our upcoming webinars on the Lux Research webpage. And thank you all for joining us today, and have a great day.